Previous class we were stopped. We were doing these graphs. So what we discussed that for strong electrolytes, whenever we draw this, then for strong electrolytes, when you extend this graphs, it will cut this y-axis. So this is called extrapolating the graph. So whenever you extrapolate the graphs for strong electrolyte, it will cut the y-axis. So this is here concentration increases in these sides, then the dilutions is increase this side because concentration and dilutions are opposite each other. So at infinite dilutions, whenever you are increasing dilutions at infinite dilutions, here dilution is at this point, dilutions is infinite. Here dilution started, so you start adding water. Here the dilution is infinite, huge amount of water you added. So this is at infinite dilutions. Okay, so at infinite dilutions you see that the values of molar conductance increases. So at infinite dilutions, what you say is that alpha equal to molar conductance at any dilution divided by molar conductance at infinite dilutions. So when concentration tends to 0, on the time alpha equal to 1, we discussed previous class. So if concentration means here the concentration is here, dilution is very high, infinite, and concentration is nearly 0. Here concentration is, let's say, infinite, and dilution is, let's say, 0. Similarly here concentration is 0 and dilution is infinite. So when concentration tends to 0, then alpha tends to 1. So if alpha tends to 1, then this equal to this upon this. So on that time on that time what that lambda m is a molar conductance equal to molar conductance at infinity. So when alpha equal to 1, and this alpha equal to 1, when it will come, when c tends to 0. Okay, this is case 1. We have discussed that when c tends to 0, then alpha equal to 1, and if alpha equal to 1, then this molar conductance upon molar conductance at infinity, and this is 1, then molar conductance equal to molar conductance at infinity. This is molar conductance at any dilutions or any concentration. So that is equal, so this value will equal to molar conductance at infinity at c tends to 0 or infinite dilutions. Okay, so if we understand this in a picture wise, then what it says, if we have the so and we are doing, so here let's say NaCl is the electrolytes. So here Na plus Cl minus, this is the, whenever you add water, so NaCl will be how it is present, it will completely dissociate. So Na plus Cl minus. Okay, this is there like this, and whenever we add the water, so here before adding water they have some, all the dissociate attraction is there. So same amount of, let's say 2 centimeter of distance between them there. But whenever we add the water, then what happened, huge amount of water came in this solutions with electrolytes, huge amount of water is there. Huge amount of water is there. So what happened in this NaCl, in between the NaCl there is 2 centimeters there, here the plus water will come, water molecules will come. And whenever you add infinite amount of water, means you add huge amount of water, then water will be huge amount of water will be there. So this Cl minus may be here. So distance between this and this increases in a huge amount distance. So it's whenever the distance between these two ions is very huge amount, let's say this is because of huge amount of water, let's say Cl minus has gone here and here only water is there. Okay, so you see the distance between at infinite dilation, when you have huge amount of water, that distance is very high. So on this time the attraction between Na and Cl minus is nearly zero. It means that at infinite dilutions this Na and this Cl minus will no attractions between them, so they behave individually because no attractions between the opposite ions is there. That's what it says, that at infinite dilutions, whenever you add that at infinite dilutions, here dilution is increases, at infinite dilutions the molar conductance of any that tends to molar infinity. So it is at, so here if the distance between them is huge amounts and there is no attractions between two ions, on that times if you find that molar conductance, then the molar conductance will be equal to molar conductance at infinity. Okay, so at infinite dilutions, that's what it says. So this we can, so this molar conductance at infinity we can find by doing extrapolating of the our graph, our slope. If you do extrapolate, then you will get that molar conductance at infinity, and molar conductance at infinity the ions behave individually, so no force of attractions between them is there. Okay, but for the weak electrolytes, if you extrapolate also, it will not touch the y-axis, it will go parallel to y-axis. So for weak electrolytes we can't do extrapolating, and you can't find that molar conductance at infinity, we can't find for weak electrolytes, but this value we can find for strong electrolyte. So what the Kohlrausch law he did, so the laws, Kohlrausch laws, what this law says, that if you want to find that weak electrolytes, by these graphs we can't find the weak electrolyte because it is not touch the y-axis. If you do how much extrapolate, because it go parallel to this, but by using the strong electrolyte, because for strong electrolyte if we extrapolate, then we can get the molar infinity value, molar conductance infinity value we will find. So using the with the help of strong electrolyte we can find the weak electrolytes. That is what is called Kohlrausch laws. And at infinite dilutions, what is that they behave individual property, they show individual property because attractions between them is very less, so they behave, the ions will behave individual property they show. Let's say if I say that you have, suppose NaCl, you know that infinity, molar infinity value of NaCl, suppose if you know, let's say x1, and molar infinity value of HCl we know, let's say x2, any value, and molar infinity value of CH3 CO and F we know, let's say x3. Then using this value, can we find molar infinity values of CH3 COH weak electrolyte? Will you able to find? So this value by graphs we can't find the molar infinity values of weak electrolytes, we can't find, but this value and this value and this value we can find. So So this value, suppose we know it, then using this value you have to find this value. So since this is strong electrolyte, so this is completely dissociate. Dissociate into Na plus plus Cl minus. And if the smaller conductance values, whenever you write, then this one also I can write this one. So in some books written like this also, this same. And whenever you are writing that, whenever you are dissociating, on that time what you write, that this, well, this just for that they whatever they given, that for whenever you like the ions we write like this. So they have given like that, then we have to assume that one. Okay, so simply they have given this for whenever you like whole molecules you write this symbol, and whenever you like for ions you have to do this footnote. You put this line. Okay, so for NaCl this value, and for HCl this also strong electrolyte, so this also completely dissociate. So this also completely dissociate, and then I will write H plus Cl minus, and this is also strong electrolyte, because if one component is strong and H comes from NaOH, where NaOH is a strong electrolyte, then the whole electrolyte will become strong electrolyte. So this is also strong electrolyte. So this is also completely dissociate. Na plus. Okay, and from that we want to find this value. So we know that at infinite dilution, this is infinite dilution. At infinite dilution, this and this everybody behave individually, means they have no any relations with this, because water has came in between, so they behave individually. So what you do, that there will be no relations with it, because they behave individually properties. So what you do, that I will add this. So I need the value of this value I need. So for that what I do, I will add this and this, then I am getting this value. So I will add, this is x1 they are given, this is x2, this is x3. Then what I do, that if I add CS, if I add the x2 plus x3, yes, x2 plus x3, it means x2 is this value and x3 is this. So if I add plus x3, and I will add this value. So if I add then this and this, I will get this one, and for this I get compound, so I will put this value. Okay, I get, with that I have also this one, and this one is also there, but I not need this value, only I need this value. So this one I can cancel. So this value we did. Sorry, this is x2 plus x3. So with this value, if I subtract with this one x1, then I can cancel that NaCl, because this is also NaCl is there. So what I do, minus x1. And if I put minus x1, then I have to subtract NaCl. So this and this cancel. So final product I get this one, which is asked. Okay, so this is equal to x2 plus x3 minus x1. So like this, by using the strong electrolytes values, I can find the molar infinity value of weak electrolytes, because for strong electrolytes they will, at infinite dilutions, they will behave individual properties. They have no any attractions between this and this. Okay, because whenever you add water, the distance between them is huge amount, so the attraction between is nearly negligible. So if nearly negligible, then this Na will behave its own property, this Cl will behave its own property. Their property is not affected by between them, because water is there. Attractions between them is decreases and they become far away of each other. Okay. Similarly, if you are take another examples, like if I take that Na2SO4, Na2SO4, let's say Na2SO4, and let's say its value is x1, and H2SO4, let's say its value is x2, and HCl is there, let's say this value x3. Then they ask that find NaCl value. How can you find? So here we are finding the strong electrolytes on values, but this value is not given to you, so you have to use these values and you have to find this value. So these all are strong electrolytes, so at infinite dilutions they will behave, these ions will behave individual property, they will show individual property because water come in between them and the distance between them increases. So let's write this Na2SO4, it will dissociate into 2Na plus SO4 2 minus. So if I put this Na2SO4, then what I have to do, this value for ions I have to write this symbol. So what is write 2, and this is at infinite dilutions. So everything is happening at infinite dilutions. That's why I write this, because I am taking this one. Okay, so this is happening at infinite dilutions. That's why they be individual properties. And H2SO4, this also going to get 2 S plus SO4 2 minus. Similarly HCl going to get Cl minus, and from here you have to find that NaCl. Okay, so how will you get NaCl? So if I add this is x1, this is x2, this is x3. So if I add this x1, I get Na, and if I add x3, then I get x3, then I get NaCl. This value I want, this one, then I get NaCl. Okay, so how I get it? So I will add x1 plus x3. Okay, then what is the value we are getting? 2 Na plus and 2 minus. Okay, if you add it, then what you get? This one and this one I want. So what I do? Okay, or we can put, so this one we get by adding this value. Okay, so from here I got these values. Although I get this value, I need this values, I need this value, but I not need this value, so I want to subtract this value. So how can I subtract this value? So this one plus x1, and whenever you add x3, then we get this value. So from here if I do that this one, then I easily subtract. Okay, but here 2 Na plus is there, but I need only one Na plus for NaCl. What this is Na plus and Cl minus. I need only one Na plus. So what I have to do, I have to divide it. So I need only one Na, but here 2 Na plus is there. So for that what I have to do, if I divide it, this one by 1 by 2, then here also I have to divide by 2. Here also I have to divide by 2, because if I do divided whole there, then you have to divide this by 2, divide by this 2, and so this also divide by 2. So this one if I write, then how can I write? This one divide by 2, okay, and this one divide by 2, okay, and this comes from this HCl, this, so here no need division, so this value, okay. Now so if I divide this, then this will cancel it up, so this is and this is here, but this is 2 is there, so 2 I have to put here, okay. So this one I have to subtract. So in these equations, this is there and this is there, but here no division, but this value is not divided by 2, so I need to subtract this value, so again I have to divide here 1 by 2, so this m to 2, this also comes to, so this value, if I subtract this value, then that is 2 to cancel up, then plus and divided by this 2, then support, or yes, it's better not to write this side because it will not flow, so I am writing down one, okay. So whenever I divide it, then only this value will come. After that, here this divided will come, then okay. Now we can cancel it, this minus, here minus is there, so this will become minus, so this cancel, and this whole minus means here also minus will come, this is minus, okay. So this and this cancel, so finally we get plus cell minus, that is going to get NaCl, okay. So using the strong, if we know the values, we can find that unknown values, whether the strong electrolytes or for weak electrolytes, because at infinite dilutions these ions behave individually, they show the individual properties, they have not affected by its respective ions. This is not affected by these ions after dissociations at infinite dilutions. So that concept we use, and we will find that unknown ions, okay. This is for molar conductance. And what happened for equivalent conductance? Let's say for equivalent conductance, that is this one. So for this, either you are doing the conductance or equivalent conductance. If this or this, here also on dilutions it also tends to infinity. So for molar conductance, equivalent conductance, same will comes. So for equivalent conductance also like such, same examples of which will take. So I will take this example. Okay. So if the same examples for equivalent conductance also given, let's say equivalent equivalence of Na2SO4 and H2SO4 HCl, okay. Let's say Na2SO4 is given to you, let's say X1, and equivalent conductance of H2SO4 is given to you, let's say X2, and equivalent conductance of HCl is given to you, let's say X3, and equivalent conductance of NaCl asks, then how will you find it? Okay, this is the same, right? Yes. So if this is given, how will you find? So for not for equivalent conductance, For equivalent conductance, coefficients are not included. This is very important points. For equivalent conductance, coefficients are not included. Very, very important. But for equivalent conductance, whenever find coefficients are not included. But for molar conductance, coefficients are included. But here, not included. Why it is so? We will discuss. Okay, so this value is very, very important. So let's say this value, whenever infinity equivalence of Na to SO4 is right, then what are we doing that at infinite dilutions? So what are we doing that? To Na plus, this we are writing like this. We write like this, but for this is for molar conductance. Okay, if molar conductance is that, but if molar equivalent conductance infinity, or we can write infinity, or I can write this one. Okay, anyone you can write. Let's say I am writing this one only. So if this is written for equivalent conductance, then what you do? This is for molar conductance, and for molar equivalent conductance, this coefficient will not return. So this is simple. Okay, so this value is not included for equivalent conductance here. That is not included. Okay, so this two value is not included here. That's the main points we have to remember. For molar conductance, this coefficients included, but for here the coefficients not included. Okay, this you have to remember. Why not included? Because let's say whenever you are doing that, we have know the relations between molar conductance and molar conductance at equivalent, that is equal to X factor. So this value molar conductance at infinite dilutions or whatever, that is equal to X, this value. So this value, this X factor is coefficients of that. So whatever you find, like if you find that Na plus 2H cam, then its coefficient also comes. This X factor means this coefficient again comes here. So this will be cancelled out. Here the coefficient is 1. So again for this equivalent conductance, molar conductance, but this X factor has came. X factor is 1. Whatever this ions, this and this, so this cancel. Okay, so whatever this comes, again that X factor means that same value will comes here. So they will cancel up each other, because this is the relations. If this is relations, then this equal to X. So with equivalent conductance, X is coming. Okay, so this and whatever this came, that will get cancelled out. Sorry, any problems? Sorry, they actually, this is what. So that will be divided. How it is coming? We know what is the relationship between molar conductance and equivalent conductance. We have discussed already relations. If we find molar conductance and molar equivalent conductance, then what is the relationship between this? So we know that this molar conductance is equal to N kappa, sorry, this is kappa upon molar, and this is kappa upon n. Okay, and this kappa cancel, then this is going to be 1 upon m and 1 upon n, so that is going to give you n by n upon m. Okay, so molar conductance of m, molar equivalent conductance is equal to n upon m, and you know that n is equal to x upon m. So n upon m equal to x, so this value is equal to x. So molar conductance equal to molar equivalent conductance into x. Okay, so this values we know. Okay, so this is the relations between molar conductance and equivalent conductance. Okay, so you are finding this molar conductance values, then this molar conductance, molar equivalent conductance equal to molar conductance upon x. Okay, that's why whenever you put these values are molar conductance values, and with molar conductance x factor is get divided, that's why this is get cancelled up. Okay, I think clear it. So this molar conductance is these values, then molar equivalent conductance is, I will erase this. This is equal to x. So if molar conductance upon molar equivalent conductance equal to x, then if molar conductance value is this, then molar equivalent conductance, I will write again in a very nicely I will write. Okay, this is molar conductance at infinite divisions of value of this is Na2 SO4 is 2. This is for this molar conductance at infinite divisions, and for molar from here what we say that molar conductance equal to molar equivalent conductance. If we write infinity this value, so this one also you can write this molar equivalent conductance equal to molar conductance at infinity upon x. So also you can write, so this value is for this, then for molar equivalent conductance at infinite dilutions will be the same as just divided by x. So this is same just divided by x, so same value, the same value just divided by x. So here x is the coefficient, so whatever the coefficient that is the x. So 2 molar conductance Na plus divided by x, so x is 2. Similarly here molar conductance is about 2 minus, and here 1, so here also 1. So the x factor will comes whenever we are doing the equivalent conductance, and this x factor is same as the coefficient, so this cancel, this cancel. So molar conductance at equivalent molar conductance at infinite is going without coefficients. Okay, that's the reason. So now if I do so now if I put all this without coefficients, because for equivalent conductance we no need coefficient, then what it will become, I will not include coefficient. This is for x1, this is for x1. Okay, so x1 I put, then I want to find this NaCl, then what I will find NaCl if I add x1 plus what I have to add, I want to find NaCl, then x1 and Cl I will get here, so I will add x3, and if I subtract by x2, simply, right? No need of coefficient you have to add. So this is x1, this is x1, and we write x2. So x2 of molar equivalent conductance is this. So if I add x1 and x3, so let me add x1 and x3. x3. So x3 is what? Yes, HCl. Okay, molar equivalent conductance of HCl. So without coefficient, without adding coefficient, so here coefficient also 1, so no problem for this case. So if I add these two, then I will get NaCl and SO4 and H is there. After that, but if I add this, then Na plus minus, but something has left, this also there. This is there. So but I only need these values, I not need this value, so this value I have to subtract. So for this subtracting this value, I will subtract x2. Okay, so from here, let's say this value is 10. So I will subtract x2. So x2 is this one, so that is going to give minus. So 2h plus I will not write, because for equivalent conductance the coefficient will not come, so I will write plus. Okay, so this and this cancel, so finally I left with Cl minus. That means sorry, this is this. Okay, so we understand that for equivalent conductance we will not include the coefficients. Why not included? Because of these relationships. So equivalent conductance is molar conductance at infinite dilutions divided by X factor upon X factor. Okay, so this is the Kohlrausch law. Okay, the Kohlrausch law says that using that strong electrolyte values, we will find that unknown values, whether it may be strong electrolyte or it may be weak electrolytes, and it mainly famous popular for using the strong electrolyte values. You will find that weak electrolyte value, because for strong electrolyte, if we extrapolate, then we can find. So in experimental we can find by extrapolating the strong electrolyte graphs. For weak electrolytes, if you extrapolate also you can find it, because it will cause parallel. Okay, so next topic is factors affecting ionic mobility. Next topic will be factors affecting ionic mobility. So what are the factors that affect the ionic mobility? So first factors is that size of the ions. So it says that if ions have the small size, then they will easily move. If small size, then speed is high, right? If anything if have the small size, then they can easily move, right? So the size of ions, without any water, that we say that crystallographic size means without water or without any molecules, only water is there. On that case we can say crystallographic size. So crystallographic size of, if we say that if you have Na, K, N plus, K plus, we have that ions, sorry, we have the ions like lithium plus, Na plus, K plus, and we have the ions, any ions like Ag plus, Au 2 plus, these ions are there. So in this case, what is the size? So crystallographic size means without water. So we say that as we move to the down of the groups, then when you group down the group, size increases. Okay, this is top to down. Size increases. So because why size increases? Because let's say Li to Li plus 2 plus, this is second period. Then in third periods, what happens that layers will comes one layers, two layers, that will add, like if I say, how can I explain? Let's say this is nucleus. Yes, so this here, let's say Li is there, then for Na it will comes in the next layer. So in between that one, this is in this layer, in between that another layers Na plus is coming. So like this, thus distance between the nucleus and this is increases, so that is size is increases. So while moving the down groups, how many would we move the down, then another layers will added up, and size will increases from nucleus to this. So from down to groups, from top to down, size increases. So if size increases, then distance between nucleus and that cations increases, so or electrons increases, means size increases. So from here size increases, so top to down size increases, means crystallographic size Li has most very less size, then Na, then K plus, then Au. Okay, this is the crystallographic size. So this size is very less. Then for hydrous radius, whatever this. So if this size is less, and if in the solutions, if suppose this is aqueous solution, then water molecule is there. So if less size, then more water molecules will get attracted. So if it more small size, so this is density equal to mass upon size. So if mass means if the size is very less, then then density will be high. So if density is high, then more water molecules will get attracted to this. So this Li plus, more water will attracted to here. So more water molecule attracted to this, then its hydrates ions will become a more, Li will become a bulky sphere, whereas Na plus is less compared to Li, less size, so less number of water molecules will attracted, means this size is less compared to Na. So if size is high, then speed will decrease. So this will become, Li plus will become hydrous radius on that time. So here the ionic mobility is also, so this is less size, so this will speed will be high. So this is high. So this size is like this. So ionic mobility will be like this, because if size is more, then size is less, then ionic mobility is high. So this. Now for hydroc radius, since ion molecules get attracted, so this will become more space because its size is less, so more water molecules get attracted, so it become bulky sphere. So now the size of Li with ionic sphere is increases, so this is high, this is high. So the ionic mobility of hydric radius will be, which is less size, that will be high ionic mobility, so this is become like this. Okay, because of this hydric radius, this size H become more, so if size become more, then ionic radius will be low, because size inversely proportional to ionic mobility. Okay, same thing if we compare for, let's say I will compare with H plus and Na plus. Okay, so for crystallographic size, size if you calculate, compare between H plus and Cl minus, Na plus, then this size is less, so this size is less and this size is more, then ionic mobility, then okay, then ionic mobility will be, so this is size is inversely by ionic mobility, so this H plus will by Na plus. This is for crystallographic. And for hydrous, so for hydrous radii, but that since H plus size is less, so more water will get attracted to this, so more water get attracted to this means this this become more bulky sphere compared to this, because this size is less, so that case that H plus is more size than Na. Then that ionic mobility is just opposite of that, so it should be, since this size is more, so mobility will less, so Na plus should be high. Okay, so this is according to the concept, but this concept is not applicable here, not applicable. Reason, so reason is explained by Kohlrausch Law, Kohlrausch ion law. But it says that if we compare, this is in aqueous solution, let's say this is aqueous solution, then only this concept is applied. Aqueous solutions where water molecule is there, water is as solvents. What it means says that, what the Kohlrausch ion job says that if we compare any ions, if you compare any ions, and that's for that same ions, if the what it says, Kohlrausch ion job, what it says that if ions are Na plus and H plus and the solvents is water, so if here this water is also ionized into this and OH minus, it means whenever you compare the ions having the solvents where the same ions is present and with other ions we are comparing, on that time this ions which have the same ions in the solvent, that always the more ionic mobility than the other ions, because of the ion jumps. How it is happen, let's say, so water is in solvent, it is like this, So whenever we are comparing this Na plus and H plus, so although ionic radius of this is high, this is less size, but what happened, this ions is not need to like that, like this in solvent is there, in solvent this type of project. So this Na plus with water molecules, water sphere, that is hydrosphere has to move here. So during moving it get so many interactions with these water molecules, so many hindrance it will get. For water, what happened that it only just has to do the job, means this HF plus, this HF plus with water molecule is there, the same as this, so it only has to jump. So this will jumps here and this will jumps here and this will jumps here, and so this only jumps. So only jumping will happens for water molecules. For the Na and ion pair, that has to go to this, through this has to go, but here it no need to move, it only do the jumping, just H plus will jump. So only jumping happen. So that the regions that H plus ions, although its size is high, but its ionic mobility will be more than other ions. So this concept is not apply for if that same solvent is present. Similarly, if you compare that NH power plus and K plus, any other ions, and in liquid NH3 solvents, liquid NH3 solvents, liquid ammonia. On that case, what happened? This NH4 plus and this liquid ammonia, the same solvent is there. So here this will be become high ionic mobility compared to other ions, because with these ions the same ions is there in the solvent. So this is dominant. So this ionic mobility will be high. So that effect is called Grott's effect. Okay. So first factor is size of ions, and different cases we see, and second factor will be temperature. So if temperature increases, then kinetic energy of ions increases, kinetic energy of ions increases, which tends to high ionic mobility. So if you increase the temperature, then ionic mobility will increases. Similarly, if you increase the temperature, then what it says, that values if you increase the temperature, then the viscosity of solvents decreases. If it decreases, then high ionic mobility will occur. Okay. Then third factor is pressure. So if pressure, if you increases, then the ionic mobility will be decreases. Ionic mobility decreases. Okay. So these are the factors on which the ionic mobility depends. So next topics we will discuss about of the transport numbers. So today after this, thank you.